Recording. Hello, and welcome to today's lecture on measurement error. In today's lecture discussion, we're going to first cover some important topics in measurement error from Chapter 6 in Freedman, Pisani, and Purves, and then we'll do a more lengthy exam review for our upcoming exam covering Chapters 1 to 6. And we're going to do a lot of practice problems today, so get ready out there in the audience with your thinking caps and get ready to respond. So there's going to be lots of questions. Those are opportunities for you to submit an answer and just try it. Don't wait and see what someone else says. Submit your answer. It doesn't matter if you're right or wrong here, but it does help you to always try. Trying is significantly associated with success in this class. So, I mean success as a passing grade you're happy with, not success as getting every individual question right. That doesn't happen for anybody. Measurement error. So, when we are thinking about measurement, we're often confronted with there's a variety of issues embedded in the topic of measurement. When measuring social variables, they're generally don't have an inherent scale embedded in the variable. So, like age, temperature, height, weight, physical variables, there's a scale we would say is embedded in the variable itself. In a lot of social research, we say, oh, I want to measure some outcome, such as a predictor or an outcome, really. You want to, and the researcher defines the variable and also then often has to develop some kind of scale or measurement to a scale to quantify the variable. And then whether your variable has an inherent scale embedded in it, like temperature, age, and of course we can, as we discussed in our lecture on the normal approximation, we can change the scale of a variable, but certain things have already a clear order of things. Number of children. They go up in intervals of 1. They don't go up in intervals of 1/2. They go up at a standard rate. So when thinking about error, we want to think about, we can think about error in this sense, the error in how we constructed the measurement. Like if I was measuring how worried students are about the exam, I could measure it in a variety of ways. I could say, are you worried? Yes or no. That variable, the yes/no response to how are you worried about the exam, would be a nominal variable. There's no hierarchy there. It's an either or, fully categorical. I could say, rate how worried you are about the exam on a scale from 1 to 10, 1 being not worried at all, 10 being as worried as I could possibly imagine being. And you would provide answer corresponding to your own level of anxiety, but your answer, thank you, your answer would be still based on your interpretation of the scale that I had laid out. And so no matter how carefully you tried to report accurately your anxiety level about the exam, a measurement, there's always some chance error. If I asked you a second time, a few minutes later, you might feel a little bit differently. Or if I asked a whole class And then I asked another class, there's always some measurement error. If a measurement is repeated, it will always come out a little bit differently. You might think, well, I'll remember what I said earlier. Maybe yes, maybe no. If you're authentically answering, you know, and this is a tricky thing about social research, is that there is this issue of when you repeat a measure, a participant might remember something. This is a fine point of experimental design we're not going to get into right now, because in today we're just thinking about measurement error at a pretty surface level. And so we're going to discuss chance error first, which is just a part of any measurement. So anytime we take a measurement, we assume there's some chance error there. Even, for example, let's say I went outside right now and I took my thermometer and I got a measure in Fahrenheit of the temperature outside. Great. Let's say it's, I don't know, 66.4 degrees right now outside. If I went out there again and then measured the temperature outside again, it's likely I would see some small error in my measurement. It might come out now at 66.3, 66.5. You know, there's always a margin of error that surrounds any actual measurement. That error is the chance error. There's always some chance error. How much is the chance error for any particular variable? Well, you don't know going in. This is why it's an issue. The best way to answer the question of how much chance error is there is to replicate the measurement. And if we replicate a measurement, then we can get a standard deviation of a series of repeated measurements. And this will be an estimate of the likely size of the chance error in any single measurement. And this is an important point we're going to revisit in future topics. So while the standard deviation of a series of measurements is telling us the standard amount of deviation expected in this variable based on our sample, it also tells us the estimated size of error in any individual measurement. Thus, an individual measurement is the exact value measured plus a chance error that you can't know exactly. You can't, for this individual measurement, you don't know exactly what the amount of chance error you have. You can estimate the amount of chance error by using the standard deviation. When we take a series of measurements, we have almost always an issue of outliers. Outliers are scores that are far beyond the spread of the rest of the data. So as you can see in the figure on the left, we've got measurements here of the the National Bureau of Standards in Washington, D.C., and their measures on grams, but this could be any, it could be any generally normally distributed variable where there's some outliers like this, and we usually see these outliers. And as we know, scores that are much farther than expected from the mean tend to skew the distribution in one direction or another. And they, at the very minimum, I mean, here we have outliers on both sides, but at the very minimum, the outliers change the spread of the distribution and of the units that describe it. And so what we see over here, and this is sometimes done in analyses, we know that we have a couple of outliers here and they're expected. So it's arguably in certain situations appropriate to drop the outliers from your distribution. When is it appropriate or not appropriate? That's a theoretical question related to individual variables and one we don't really have a lot of time for today. But in short, when you have outliers and it depends on the distribution of outliers. If there's just one or two, like there are here, then it's more reasonable to drop the outliers. If we had a set of outliers over here where maybe there were outliers all bunched at the top of the distribution, then it would be worth looking into that in a more statistically complex way, because it might be that there's something happening or some other third variable that has influenced those outliers and their scores. And the other big topic in this chapter was bias. Bias is a systematic error. And it's important to remember that bias affects all measurements the same way. It pushes the measurements in the same direction. And that's different from chance errors because chance errors change from measurement to measurement. A chance error is random, not systematic. Bias is always systematic. And this is the difference between error and bias. When we do statistical analyses, we have measurements, estimations to help us deal with chance error. For example, the standard deviation, you'll see when we use that later in calculations, we are using it to help account for the chance error, the random error that's just expected in our variable. Whereas bias, in order to eliminate bias, we need to examine experimental procedures and systematic influences that might be pushing participants' responses or pushing data in a particular direction. One source of bias that I know probably all of my nurses out there and many of the rest of us are familiar with is the effect of getting a blood pressure in clinical scenarios. So oftentimes there's a bias towards patients having slightly higher blood pressure in a clinical context than they might in other contexts because the clinical context itself is stressful for them. And that stress pushes blood pressure up. Clinical contexts don't, it's a systematic error, the bias, because it pushes all these blood pressure measurements in the same direction. Oh, white coat syndrome. Thank you, Molly. It was on the tip of my tongue, but I couldn't quite find it. Yeah, they're scared of the white coats. We don't see the bias going in the other direction. It's not that the patients are randomly have lower blood pressure at the doctors. No, it always goes in the same direction. It's a systematic error or a bias. And so we can refine our understanding of individual measurement by factoring in this additional piece. The individual measurement is whatever the exact value is, plus that chance error we previously discussed, and now bias, which would be systematic. Although it's important to remember that when you do have bias in your variable, it's pushing the measures in the same direction. And since all the measurements are going in the same direction, this affects some measures of central tendency or variability more than others. So if you push all the measurements in the same direction, sure, your mean or is going to go up, but you're by the amount of the bias. But it hasn't changed the distribution of the scores. And one final point on this, you can't detect bias by just looking at the data. You have to, again, take a more philosophically grounded or a more detailed look at your experimental design and the research administration to find things like this kind of bias. So, any questions about those topics before we get into our review exercises? There's only a handful here, and I do want to, we're going to spend most of our time reviewing for the exam, but let's go through these real quick. Our first exercise is a true or false. An experienced scientist who is using the best equipment available only needs to measure things once, provided he doesn't make a mistake. After all, if he measures the same thing twice, he'll get the same results both times. What do you think? Is that true or false? It's false. Absolutely. We just discussed how any measurements are not going to come out the same twice, generally speaking. There always is a little bit of error. There's a saying in, I don't know, construction or carpentry, people in building things, measure twice, cut once. Why measure twice? Because when you take multiple measurements, you're more likely, if you're going across those measurements, to get the best estimation of the real location because you account for more chance error. The more measurements you take, the more chance error you can account for. Oh. Now we're looking at problem 2. A carpenter is using a tape measure to get the length of a board. Boy, no wonder I had that example in my mind. So you're using a tape measure to get the length of a board. What are some possible sources of bias here? The tape measure itself. And so aspects of the tape measure first are some things that might affect our bias. Like I have a tape measure that has where it starts a little bit in. So there's like a 1/4 inch. And if I have to remember when using that, I can't start at the very end of the tape measure. I have to account for that 1/4 inch. And not accounting for it, sure, that would be a human error. But the tape measure itself could have error. I have some cloth tape measures, and a cloth tape measure has a particular type of bias. Let's talk about that on part B here. Which one is subject to more bias, a steel or, yeah, thanks, Molly. A cloth tape measure could stretch. How can you know how much it stretches? Well, you could compare it against another tape measure for comparison. But what if that other tape measure has measurement error? I mean, ultimately, you could pick, if you really wanted to know the true amount of error in your cloth tape that may have been stretched, you might want to measure it against a couple of other tape measures to assess its measurement. Presumably a steel tape would be the most reliable. I have some wood measuring rulers and things. And although I think maybe wood is reliable, it does change over time. So, you need to consider that when you're thinking about the bias that might be in any particular material. So would the bias in a cloth tape change over time? Yeah, of course. Yeah, thank you, Stephanie. This is a great example. If a fabric store used a cloth tape measure that stretched from 36 to 37 inches, every time they sell to a customer, they have an extra inch tacked onto it. So they are have imposed some systematic bias. This is a systematic error or a bias in their measurement because of their biased cloth tape. Would the bias in a cloth tape change over time? I would argue, yes, it does. The tape warps, it stretches, it probably stretches more in the beginning than it does later because the cloth loses elasticity over time. True or false? Bias is a kind of chance error. True or false? Peanut gallery. False, that's right. Bias is a systematic error. Is chance error just a kind of bias? Or I guess the question is, chance error is a kind of bias. True or false? Yeah, it's still false. Chance error is a type of error, and bias is a kind of error. Bias is a systematic error. And finally, measurements are usually affected by both bias and chance error. Is this true or false? Yeah, this is true. Measurements are affected by both chance error and bias. As we see here, an individual measurement is equal to the exact value plus whatever bias there is and chance error. Now we've got a yardstick. You send your yardstick to a local laboratory for calibration. Okay. Asking that the procedure be repeated 3 times, and they report these values. If you send the yardstick back for a 4th calibration, would you expect to get 36 inches, give or take 0.01 inches, 0.03, or 0.06 inches? Well, to answer this, we need to first look at the amount of deviation in our values, our first 3 values. So we should get a mean of these values, and then we could get the deviation from the mean. Eyeballing this, I can see the mean would be 36 inches, I think, or approximately. Whatever the exact mean is. Yeah, the expected error would be 0.03 inches or so. Why is that? Well, because I can see that I have an error of about 0.03 inches on one of these, an error of negative 0.04 inches here. So I would expect the error to, again, be about the same as it was before. And last but not least, we have 19 students in a beginning statistics course who were asked to measure the thickness of a tabletop using a vernier gauge reading to 0.001 of an inch, or 1/100th of an inch. 1,000? Yeah, 1,000th of an inch. Each person made 2 measurements. I forgot to copy the next page. Sorry about that, but it is on, or I'll pull it up for us in a moment. Did the students work independently of one another? Well, we have to look. So here's our measurements. We know each person made 2 measurements, and we can see their measurements here, first and second. What happened with these people, person 1, we can see most of these measurements are within approximately 0.1 or 1.3 something. But we've got 2 people who have measurements way outside of the scale. 13.26. What happened there? I think that these people may have, that's right, misplaced a decimal. This is or maybe they didn't know how to properly read the tape measure or the vernier gauge, or exactly they have used the wrong units. The point I'm getting at is that they didn't just make a chance mistake, they systematically made the same mistake in each measurement, and moreover, person number 10 made the same mistake, or worked with person number 2 and didn't do their measurements independently. So in answer to A, did the students work independently of one another? It looks like most of them did, but it seems pretty obvious that students 2 and 10 didn't. Now we have part B. Some friends of yours do not believe in chance error. How could you use these data to convince them? Well, we could simply point out how nobody got the same answer both times. Even the same person measuring twice had some variation in their measurement each time. And that's due to chance error. We can see that the change in the person's first and second measurement, it doesn't always go in the same direction. We can see here, if we look at person 11, their first measurement and their second measurement are, the second one is up by 1/100th of an inch, whereas if we look at person 12, their second measurement is up by 2/100th of an inch. Other participants have measurements that went down, like 14. On their second measurement, it was down by 2/100ths of an inch. So this is the very definition of chance error. It goes in both directions. It doesn't just go in one direction. Okay, and that's all for measurement error for now. We're going to discuss some other types of error in future chapters. But this one is just to help you get a grasp on measurement itself and some of the issues that are involved in even measurements that we think of as being very precise. Okay, any questions about measurement error before we move on? Because we're not going to review this topic again in the exam review. Okay. In our next part, we're going to go over the exam review. and some of the special exercises.